Hey everyone, welcome back to my YouTube channel, Act 1, The Anomaly. Look up into the night sky, what do you see? A familiar companion. A radiant orb that has guided sailors, inspired poets, and illuminated our darkest hours for millennia. It is the moon, our closest celestial neighbor, a constant presence in humanity's story. Yet, despite its familiarity, the moon harbors one of the most profound mysteries in all of astronomy, its very origin. How did this colossal sphere come to orbit our planet? Where did it come from? The answers, as we are about to discover, point to a cosmic catastrophe, a collision of worlds, and the ghost of a lost planet named Theia. The moon is no ordinary satellite. When compared to its peers across the solar system, it is a true anomaly, a cosmic outlier that breaks many of the established rules for how moons should behave. It acts less like a subordinate moon and more like a planetary partner. Consider its size. Our moon is remarkably large compared to its parent planet. With a diameter of approximately 3,474 kilometers, it measures more than a quarter of Earth's own diameter. This makes it the largest moon in the solar system relative to the size of its host planet. This ratio is far greater than that of the gas giants. For instance, Jupiter's largest moon, Ganymede, is just 1/25th the size of its host planet. The same holds true for Saturn and its moon Titan. While the Pluto-Charon system has a closer ratio, they are a dwarf planet system. Among the major planets, the Earth-Moon pairing is unique, leading some scientists to refer to it as a double planet. This sheer scale immediately sets our moon apart, suggesting a formation event far more dramatic than the gentle accretion of dust and gas that typically forms smaller satellites, or the gravitational capture of a passing object. But the anomalies don't stop with size. The moon's very substance is a puzzle. Its density is just 3.34 grams per cubic centimeter, far lighter than Earth's 5.51. This tells us the moon is missing a key ingredient, a large, dense iron core. It appears to be made mostly of lighter, rocky material, as if it were skimmed from the surface layers of a larger object. Then there's its orbit. Most large moons in our solar system circle their planet's equator, but our moon doesn't. It orbits closer to the ecliptic plane, the same plane in which Earth orbits the Sun. This strange orbital tilt defies conventional models of moon formation and capture. Perhaps the most profound mystery comes from the Apollo moon rocks. Chemically, they are isotopic twins to rocks from Earth's mantle. If the moon formed from a collision, it should be a mix of Earth and the impactor, not a near-perfect match. This discrepancy is a major scientific puzzle. Together, these anomalies, size, density, orbit, and composition, all point to a single dramatic conclusion. The story of our moon is the story of a cosmic catastrophe. It suggests that the moon is largely made of lighter rocky material rather than the heavy metals that dominate Earth's interior. Then there's its orbit. The moon's orbit is tilted by about 5 degrees relative to Earth's orbital plane around the Sun, a subtle but significant detail that challenges simple formation scenarios. If it had simply condensed from the same cloud of material that formed Earth, we might expect a more aligned orbit. For centuries, these peculiarities fueled speculation. How could such a massive, low-density body with its unique orbital dynamics have come into being? Was it a captured rogue planet? Did it spin off from a rapidly rotating Earth? Or did it form alongside Earth, a twin born of the same cosmic dust? Each traditional explanation, when scrutinized against the growing body of evidence, crumbled, leaving scientists scratching their heads. The moon, in its silent vigil, held its secrets close, defying easy answers. But the universe in its grand design often leaves clues, subtle whispers of past events embedded in the very fabric of celestial bodies. And it was by meticulously collecting these whispers through the lens of telescopes and the analysis of moon rocks that humanity began to piece together a truly astonishing story. A tale of a cosmic impact, a cataclysmic birth, and the lingering shadow of Earth's lost sister planet, Theia. Act 2. The first clue's asterisk for much of history. The moon's origin was a subject of philosophical debate and wild conjecture. A scientific inquiry advanced. 3 primary hypotheses emerged to explain our moon's existence, each attempting to reconcile the observed facts with the laws of physics. The first was the fish theory championed by astronomer George Darwin, son of Charles Darwin in the late 19th century. This theory proposed that the early Earth was spinning so rapidly that a bulge formed, eventually tearing away to become the moon, much like a blob of clay flung from a potter's wheel. Opponents pointed to the Pacific Ocean basin as a potential scar left by this dramatic separation. However, calculations quickly showed that Earth would have needed to spin impossibly fast for such an event to occur, and the physics simply didn't add up. There wasn't enough angular momentum in the Earth-Moon system to support this idea, and the physics simply didn't add up. There wasn't enough angular momentum in the Earth-Moon system to support this idea. Following the co-formation theory, another idea gained traction, one that seemed elegantly simple at first glance: the capture theory. This hypothesis proposed that the moon wasn't a native of our neighborhood at all. Instead, it was a fully formed planetary body, a lonely wanderer that originated somewhere else in the solar system, perhaps forming closer to Mars or even drifting in from the asteroid belt. The theory suggests that, by a stroke of cosmic luck, this rogue body passed just close enough to Earth to be ensnared by our planet's gravitational pull, becoming our permanent satellite. On the surface, this idea had some compelling advantages. It neatly explained the significant differences in composition between Earth and the Moon, as a body formed elsewhere would naturally be made of different stuff. It also provided a straightforward explanation for the Moon's unusual orbital inclination. A chaotic capture event could easily result in such a tilted, non-aligned orbit. However, when scientists began running the numbers, this elegant theory started to fall apart. The physics of gravitationally capturing an object as massive as the Moon is extraordinarily difficult. Think of it like trying to catch a speeding bullet with a butterfly net. The window for a successful capture is infinitesimally small. For a capture to occur, the passing Moon would have needed to lose a tremendous amount of orbital energy at just the right moment. Without this energy loss, there are only two likely outcomes. If its trajectory was too direct, it would have ended in a cataclysmic collision. If it was even slightly too fast or too far away, it would have been gravitationally slingshotted, flung away into deep space, never to return. Even if we imagine a 1 in a billion chance of a perfect capture, the theory faces another major hurdle. Such an event would have inevitably placed the Moon into a highly elongated elliptical orbit. While tidal forces would gradually circularize this path, detailed models show this process would take far longer than the age of the solar system to produce the remarkably stable, nearly circular orbit our Moon travels today. Because of these insurmountable problems in celestial mechanics, the razor-thin probability of a successful capture and the subsequent orbital inconsistencies, the capture theory, while intriguing, has been largely set aside by the scientific community. It simply asks for too much luck. The third theory, co-formation or condensation theory, posited that the Earth and Moon formed simultaneously from the same swirling cloud of gas and dust, much like a binary planet system. In this scenario, the Moon would have accreted in orbit around the naant Earth. This theory could explain the Moon's proximity to Earth, but it struggled to account for the Moon's lower density and its relative lack of iron compared to Earth. But it struggled to account for the Moon's lower density and its relative lack of iron compared to Earth. If they formed from the same primordial material, their compositions should be far more similar, particularly in terms of metallic content. Also, it didn't easily explain the angular momentum of the Earth-Moon system. By the mid-20th century, the classic explanations for the Moon's origin were crumbling under scrutiny. The Fission Theory, which suggested the Moon was spun off from a rapidly rotating early Earth, required a spin rate that was physically implausible. The Capture Theory, proposing the Moon was a wanderer snared by Earth's gravity, struggled with the incredible odds against such a perfect, stable capture. And the Co-accretion Theory, where Earth and Moon formed together, couldn't account for why the Moon has such a tiny iron core compared to Earth. The scientific community was at an impasse, in search of a more robust explanation. The catalyst for a revolution in thinking came directly from the Moon itself. The Apollo missions had returned hundreds of kilograms of lunar rock, and this priceless ground truth was painting a complex picture that no existing theory could fully explain, particularly the Moon's strange chemistry and the high angular momentum of the Earth-Moon system. The turning point arrived in the 1970s thanks to the insights of two planetary scientists, William Hartmann and Donald Davis. While modeling the formation of planets, they realized the early solar system was a chaotic shooting gallery. Massive collisions weren't an anomaly, they were a fundamental part of planetary development. This led them to ask a revolutionary question: what if the Moon wasn't formed gently, but was instead born from a catastrophe? In 1975, they published a paper proposing what would become known as the giant impact hypothesis. Their radical idea was that about 4.5 billion years ago, a protoplanet roughly the size of Mars, later named Theia, slammed into the young Earth. This wasn't a head-on collision, but a cataclysmic glancing blow that blasted a colossal cloud of vaporized rock and gas into orbit. This single violent event offered elegant solutions to many of the long-standing puzzles. The intense heat of the impact would have created a short-lived magma ocean, vaporizing volatile elements and explaining their scarcity on the moon. The ejected material, largely derived from the outer rocky mantles of both colliding bodies, would explain the moon's lower density and lack of a large iron core, as Theia's dense core would have merged with Earth's. And crucially, the sheer energy of the off-center impact would also impart the necessary angular momentum to the Earth-Moon system, accounting for its unique orbital dance.